What's up, peoples? This video is to help you with work energy problems that involve springs. Springs are not a big deal. They're just another form of energy. And springs are let me try that again. Springs are usually located at the beginning or the end of the story. So usually there is a mass that is compressed a spring in the beginning and it's launching it, or there's a spring in the end of the story and the spring is stopping the mass. I don't think we do any problems where there's two springs. So in this case, we have a spring launching a mass across a horizontal surface that has friction, and then it goes up an incline that is frictionless. You're welcome. That makes the problem easier. Otherwise, there'd be multiple works. And we want to know the speed at the top of the incline. So here we go. As by now, you should know, because if you don't know, we need to talk. You write out the work energy theorem, because that's what we do. So we have the initial kinetic energy, initial potential energy, and now the initial spring energy, or elastic energy, sometimes referred to as. You might see an E there, equals kinetic energy final, plus gravitational potential final, plus spring energy final. Also, I noticed in my picture that it does end up higher than height 0, so I'm going to do H equals delta D sine theta. We've talked about this in class many times. That's 3 meters times the sine of 18 degrees. Let me do a little mental math there and get 0.927. That's right, I did sine 18 in my head, if you believe that. Back to this. What do we cross off? Well, is it moving initially? No. Is it above height 0 initially? No. New question. Is the spring initially either, doesn't matter either, stretched or compressed? It could be either one, but is it either one? Not is it one or the other, and we have to guess which one. The question is, it's yes or no. If the spring is either stretched or compressed, then we say yes. And in the beginning, it happens to be compressed, so we leave that energy. Is there work being done? Yeah, there's friction, and only one friction. You're welcome. I wanted to put it on the other incline. Is it moving in the end? Yeah, we're solving for that, silly. Is it above height 0 in the end? Yep, we're going to leave that there. And is the spring compressed in the end? No. I had a student in the past who said something pretty insightful. Believe it or not, students say things that are insightful. And they said, can we just assume that whenever the mass is touching the spring, that the spring has energy? And I was like, you know what? I think that works. So in the beginning of the story, the spring is being touched by the mass, and yeah, it's compressed. At the end of the story, when it's way up here at the top, it's not touching the spring, so it doesn't have that energy. From here, we can pull down our math. This is 1/2 kx squared, where x is how much the spring is stretched or compressed. The work done by friction at this point is negative mu times the normal, which is mg. Don't forget the delta D. If you're not sure where that comes from, please see earlier videos related to work and energy. 1/2 mv final squared for our potential kinetic energy, plus mgh final. Careful here, ladies and gentlemen and peoples. Some of you might want to cross that mass out, but that's a terrible thing to do. Is there a mass in every term? No. So you cannot divide mass out of every term. Let's do a little math, shall we? Spring constant, I believe, was 4,000 newtons per meter. Initial compression was 0.2 meters. Don't forget to square it. Minus the work done by friction, which is 0.15, times the mass, times 9.8. Don't forget the distance, which I believe is 4 meters, equals 1/2. The mass is 5 kilograms. We don't know the final velocity. That's what we're looking for. Plus 5 kilograms, 9.8 meters per second squared, and our height was 0.927 meters as I squeeze that down the side of the page like an amateur. As you know by now, please don't just go from here to an answer. I have no idea what you did wrong. I need you to break it down. Like when you do the math here, this is 80 joules. This is 29.4 joules. On the other side, we have 2.5 kilograms. I did the 1/2 times the 5. Final velocity squared, plus 45.4 joules. From here, if you go to the answer, I'm okay with it. And I got an answer of 1.44 meters per second. So that's it. Springs aren't a big deal. You're just a new form of energy. So let's recap this puppy and see what I have to say. Basically the same strategy as mentioned in previous videos. You're going to write the work energy theorem. You're going to cross out the energies that we have or don't have. And apparently Microsoft just encountered a problem. Like I care. This video will not be edited. You write out the work energy theorem as you've seen in green here. The same things as before, but because there's a spring in the problem, we add spring energy. The question is, initially, is the spring either stretched or compressed? Yes or no? If yes, leave it there. If no, cross it off. It's that simple. Same thing at the end. And as mentioned earlier, I've had a student in the past who said, can we just assume when the mass is touching the spring, that's when we have spring energy? I love it. It works. You can use that as well. And the expression for spring energy is 1/2 kx squared, where x is how much it is stretched or compressed. That's why we ask if it's stretched or compressed. And that's about it, peoples. Short video on how to deal with springs in problems. I hope it's been helpful in some way, shape, or form. I would probably give this video 3 out of 5 stars. Wouldn't change a thing.